Kia ora and welcome to this video on question 2 of the 2019 Scholl Calc exam. The first two parts were algebraic questions, the third's a nice short integral problem, and the fourth is a tricky, or fairly tricky geometric proof. It's just a little bit different. Because it's at the start of the exam, the questions tend to be a bit shorter and a little bit easier than the ones at the at the end where they're a bit harder. Okay, so the first question, when we're talking about imaginary roots, we're thinking discriminant, the thing that's underneath the square root in the quadratic formula. The problem, of course, doesn't look like a quadratic equation, but we can play around with it. So first step is to square both sides. And I'm going to do my answer is going to look a little bit different to the schedule. It will definitely look different if I write the question out wrong. The reason being, I'm taking the method here, which I think a number of students would have tried, and that's to square both sides of this. Before I think about that, normally you move one term to the other side before you square. However, with this problem, it makes sense to square it as it is. What we've got there is an a minus b all squared, which expands to a squared plus b squared minus 2ab. And the reason why I'm squaring both sides as is because the terms, the way they've made up, x minus 2 over x in the reciprocal, when we times those together we get 1, and so squaring both sides actually simplifies. Okay, we get the first term squared, which is itself without the square root, and then the second term squared, and then minus 2 lots of the terms multiplied together, which, like I said, was equal to 1, and then the right hand side is k squared over 16. Okay, I'm going to tidy up the fractions. I'm going to put the fractions together. So I've got x minus 2 all squared plus x squared all over x times x minus 2. I'm going to move the minus 2 to the other side, k squared over 16 plus 2. I'm going to cross multiply and expand as I go. So x squared minus 4x plus 4 plus x squared equals k squared plus 32 all over 16 times by x times x minus 2. Okay, if you need to pause at any point in time to understand the algebra I've just done, please do so. But we've got a quadratic equation, which is great. Times everything by 16 to get rid of that 16. There's a 2x squared there, so it's going to make 32x when I times 32x squared. I've got minus 64x plus 64 k squared plus 32 x minus 2. And that right hand side expands to, after a little bit of work, k squared plus 32 times x squared minus 2 lots of k squared plus 32 times x. This is definitely a more long-winded approach than the mark schedule, but like I said, it's probably a method that students would have taken. Notice that there's a 32x squared on both sides of the equation. So we've got minus 64x plus 64 equals k squared x squared minus 2k squared x minus 64x. It's brilliant. Those cancel as well. We're left with a quadratic equation that's fairly tidy. And we were looking for imaginary roots. So what values of k make this problem have imaginary roots? So if we use a discriminant, b squared minus 4ac, the b part is the number that's in front of x, minus 4 lots of k squared times negative 64 is equal to 4k to the 4 plus 256k squared. Now that is never negative. Okay, even powers, so no matter what you choose for k, you'll never get a negative number out of that. So you could say that this is greater than, what did we say about k? K is a real number, so k could be 0. But this is greater than or equal to 0. It's never negative. Now just remember my students coming out of this exam going that they tried this problem over and over because the question asked them to find values of k for which the problem had imaginary roots, and the answer to the question is there are actually no values of k. So the examiner trolled the students once again. Therefore, there are no real values of k, which give the equation imaginary roots. Okay, second problem is a nice system involving logs, log base 10. So let's rewrite the problem out. Log base 10 x squared plus y squared. I mean, logs are not covered in that much detail. Oopsies, I was going to jump to the first part of the answer. It was a 1 to begin with. Logs aren't covered that much in the complex numbers external. They are covered in level 2 calc, and then the log rules themselves are on the formula sheet, but you do need familiarity with them if you're wanting to solve a problem like this. Okay, so first thing is we can't just get rid of the logs, because if that was possible, if I could just go, cross, 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 then why would the problem have been written out the way it was? That would be equivalent to saying, hey, Pythagoras' theorem, why are the squares even there? We just get rid of them. Who cares? Don't need them. So of course that's mathematically wrong. We can't do that, and we can't just cross off the logs. But what we can do is rearrange equation 1, or rewrite it. Log base 10 of x squared plus y squared. I'll just leave that for now. I'm going to write 1 is log base 10 of 10. And that's the little catch in this. Because then we have two logs added, which by one of the log rules is the log of the product. And now there's a log on both sides of the equation, just the one, so then I can cross them out. What I'm actually doing is taking 10 to the power on both sides, because 10 to the power is the inverse function of log base 10. So those cancel each other out, and the equation simplifies to x squared plus y squared equals 130. Okay, now equation 2, the two logs on the left hand side subtracted is the log of the division, and then the right hand side, the 3 that's there, I can write that but with the 3 up the top. That was one of the log rules you would have learnt in level 2. So I can write that as log 10 of 2 cubed, which is 8. And we can do the same thing with the logs. They cancel off if there's 1 on either side. X plus y over x minus y equals 8. Cross multiplication, x plus y equals 8 times x minus y. And if you rearrange that, you end up getting 9y equals 7x. Or y is 7/9 of x. That can go back up into the original equation 1. Make a substitution. Therefore, x squared plus 7/9 of x all squared is 130. Now, times the whole thing through by 81 is my preference. I've got 81x squared plus 7x squared equals 10530. Divide, add the like terms is 88 and divide by 88. Oh my goodness, that's a terrible algebraic mistake. It's not a 7. If you spotted it, well done. Give yourself a fruit burst, as I'd say in my class. 49. Then add them together. You get 130. Divide both sides by 130. Back to 81. So you've got x squared is 81. X is plus or minus 9. And therefore y is plus or minus 7. Using that equation. Then you go back to the original problem, as you always will in scholarship, and check whether they both work. You see here that x plus y must be positive, otherwise the log is not defined. So that leaves, must rule out the negative solutions. The only solution that works is 9, 7. Okay, the negative one doesn't work. Alrighty. Third question, finding the area of this loop. It's easier if we just find this area here. Okay, and we just times the answer by 4. So to find that area, what I want to do is find this function f of x and then integrate f of x with respect to x between 0 and 1. Okay, you can quickly prove that when x equals 1 you get a y value of 0, so that it's not like the graph is misleading you or anything. And if I rearrange the equation, because I've got y squared is x squared minus x to the 4, the function that I'm integrating is the square root of x squared minus x to the 4. And it's the positive square root because I'm taking the top branch. If I take the negative square root, I'm talking about the bottom stuff. Okay, so I want to integrate that between 0 and 1. And like most Scholar problems, there's just a small trick in the integral that makes it harder in a level 3 problem. So I want it 4, she'll set it up better, area enclosed by the loop is 4 times integral between 0 and 1 of this function x to the 4, so x, x squared. X squared minus x to the 4. Okay, so it's important that you realize how reverse, or you know how reverse chain rule works. So a real common student mistake is to go, oh okay, yep, that's power of a half. So the teacher told me I just increase the power by 1 to 3 over 2, and I divide by 3 over 2, and maybe I divide by the derivative of the inner function as well. Absolute nonsense, doesn't work. It works in all NCEA problems because the inner function, which is this Quadratic Equation, it won't work in this question because the inner function is not a linear function. In NCEA problems, it's like, I want you to integrate this to the power of a half. And you can do what I said before. You can increase the power to 3 over 2, you can divide by 3 over 2, and then you just have to also divide by the derivative of the inner function. So it actually works. And most NCEA problems are like that, where the inner function is a linear function. Okay, but if we do the similar thing with this problem, we'll get something that's absolutely nonsense. Okay, so how do we do this? There's a sneaky trick to it, as I said. The denominator, not the denominator, the thing underneath the square root has a factor of x squared. If we pull that out and then pull it out of the square root, So I'm going to make it x squared times 1 minus x squared, and then I'm going to pull that out the front as an x. Your thing simplifies to this, and now a u substitution would be helpful. If you don't notice the reverse chain rule here, a u substitution is quite good. If we make this bit here equal to u, then du is equal to minus 2x dx. That's me differentiating the substitution. And therefore, if I put a minus 2 here, and then divide by minus 2 there, okay, so I've times by minus 2, then I've divided by minus 2, so I've actually done nothing. What I have achieved, though, is that the minus 2x term and the dx can be swapped out as du, and the only thing that's left is the square root of u, which is u to the half, and I simplify the integral completely. I've also got to change the limits, x equals 0 and x equals 1. I need to find the values of u. So when x is 0, the u value is 1, and when x is equal to 1, the u value is 0. If that makes you uneasy, the fact that the top limit is lower than the bottom, you can get rid of the minus in front of the 2 and then switch the limits back around. Essentially what that says is if you integrate something backwards, you'll get the negative of what you should have got. Okay, and we've got that, and then we anti-diff it. U to the 3 over 2 divided by 3 over 2 is the same as timesing by 2/3. Between 1 and 0, and we've also got a 2 there. Okay, and then we sub in the 1, 2/3, sub in the 0, we get 0. So it's 2 times 2/3 minus 0, or 4/3. That's the area of the loop. Alrighty, the last question I built up. I gave you a bit of suspense here. It's not the easiest, thing to do here. But what we need to think about is the structure of this. Like, what is PA dash over AA dash? Where is that? So if I just look at, maybe change up some colors here. We'll go with yellow and gold. So PA dash is this dude, and AA dash is the whole length there. Okay, and then it's a similar thing for the other one. So PB dash over BB dash. PB dash is this dude, and that's over the whole thing there, and so on. Now what you need to realize with this problem that makes it a sneaky question is that if you were trying to find the area of this triangle, okay, so let's consider that triangle there, the area of triangle BPC. Well, it's half base times height. So we'd go a half times base, which is BC, times the height, which is this length here. I don't know, let's just call it H. But what you've actually got are similar triangles. If you look at this little triangle in here versus this big triangle there, they have the same angles because they're both 90 degrees. I've made them altitudes. They've both got the same slope. They both share that angle. So they're similar triangles, which means that the height that little h that I had, is actually just the ratio of the sides of the triangle. How am I going to make this easier to understand? If I say that little h and then this big H here, right? Then little h over big H is equal to little PA dash over big AA dash. So the area of BPC is a half BC times PA dash over AA dash times capital H. And the only thing that's useful in achieving is that I've got that PA dash over AA dash thing appear. Okay, so the next step is to do that for all three sides of the so I've just found the area of that triangle BPC. If I do it for the other sides, I've got the area of APC. I'm going to get rid of all my annotations and we'll just look at that side now. APC. Okay, again, that's going to be half base times height. So half times AC. I'm going to make that the base, and this is going to be my height. And like the same logic as before, that height is going to be the ratio of PB dash over BB dash times some total height. Call it H2. And the area of the third triangle, which is area of the left hand side, the area of ABP is a half side AB times the ratio. Okay, I'll make my height down there. PC dash over CC dash times H3. Okay, so what have I achieved in all that? It doesn't look like much, but if I add those three areas up, I get the whole thing. So I've got a half where is this actually going? Because I've got H1s, H2s and H3s in here. Oh, I've led us down the garden path a little bit. No. Start again. Sorry, team. Okay, start again on this triangle. Okay, the area of that triangle, in the marking schedule they call it X, they use this notation X1, right? But if I say area of triangle BPC, okay, it is a half BC times the height of that triangle, which we'll call little h like I did before. Okay, now that area, that triangle is similar to another triangle that's in the diagram. And the reason for it is if I now consider the whole triangle, well, what's the area of that? The area of the whole triangle. ABC. Well, that's a half, same base, just different height. So if I divide these, the halves cancel, the BC's cancel, then I get this little h over capital H thing. And little h over capital H, which is what I had before, is equal to PA dash over AA dash. Because of the similarity of those triangles, it's that side over that side. Similar triangles. Okay, so if I do that for all three of the sides, now we're onto something. So that right hand side area APC divided by area, the whole triangle again, ABC, it's going to be half AC times some little h, different little h, so that's where I'll go with the ones. And that one there is going to be PB over B dash over BB dash. And then the last one, area, is the left-hand side triangle. This one, APB. But if I divide that by the total area, okay, APB, if I drop that height down there, that's my H3, half AB times H3. And then I compare it to that side, capital H3, times capital H3, little h3 over capital H3 is the same as PC dash over CC dash. Okay, so if I add those three areas up, they've all got the same denominator of ABC. Area BPC plus area APC plus area APB all over area APC. Well, the three areas that I found, when I add them up, is the total area. So that equals 1. And that there is the left-hand side, which equals 1. So that's the proof done. If you're looking at that going, oh my goodness, that's insane, unless you've got a good foundation of geometry, which, to be honest, most NCA students don't, I wouldn't freak out in a Scholl exam. I would honestly move on and deal with the other problems, and if you've got time at the end, come back. If you're aiming for top scholar, then there'll be a few problems like this in each year's exam, but don't let that put you off the rest of the paper and what you can do. It's not representative of every single question in scholarship. There's a lot that's actually doable. If we think about this question as a whole, the first question involved discriminant and quite heavy algebra, at least the way I took. The second one was quite nice. So a few log rules and a simultaneous equation. And the third one was just finding an area. The thing that was a little bit tricky was playing around with the integral and making a U substitution. But don't freak out about that last question, because to be honest, it's quite a mean problem and probably would have sorted out the top students. See you in the next video.